Hello there. I'm so glad you found your way to this quiet harbor. As the stillness of the night settles around you, let your imagination drift far beyond the safety of our home. Tonight, we are voyagers sailing into the deeper, wilder currents of the cosmos. We will drift past worlds that defy logic, places where rain falls like shards of glass, where shadows stretch for eternity, and where the winds sing a fierce, ancient song. We'll observe these extreme, beautiful monsters of the universe from a safe distance, marveling at the strange science that sculpts them. If exploring these dark wonders brings you a sense of calm curiosity, a gentle like and subscribe helps other sleepy souls find their way here. Now, wrap yourself in the warmth of the dark. We'll begin our journey together. Let your mind float upwards, weightless and free. We are leaving behind the soft blue glow of our home, drifting out past the moon, past the quiet sentinels of our solar system, and into the deep, velvet ocean of interstellar space. It is vast here, silent. The darkness is not empty. It is a canvas filled with galaxies spinning like pinwheels of light and planets that hold mysteries older than time itself. Some of these mysteries are beautiful, but others are wild, untamed, and frighteningly magnificent. Beyond the warm, protective embrace of our sun, the universe hides places that defy the gentle logic of our daily lives. Worlds so extreme that they feel less like reality and more like the fragments of a vivid dream. Imagine, if you will, worlds where the rain does not nourish the soil, but falls as shards of glass. Imagine skies swallowed by endless, suffocating darkness, or surfaces that bubble and breathe with the heat of molten lava. These are not the calm, blue marbles we picture when we think of peace. These are the universe's most fierce creations, the terrifying planets where the environment is so harsh that life, in any fragile form we know, simply could not find a foothold. But tonight, we are safe. We are merely travelers in the realm of thought, observing these giants from a distance, shielded by the comfort of your own warm room. Our journey takes us to the very edge of understanding, where every star we pass illuminates just how strange and formidable space can be. Drifting through the constellation Vulpecula, the little fox, about 64.5 light-years away from where you rest right now, we approach a world that looks deceivingly serene. This is HD 189733b. From afar, it glows with a deep, stunning cobalt blue, a color so rich and familiar that it might remind you of Earth's deepest oceans on a sunny day. It looks peaceful. It looks like a marble of sapphire resting in the black velvet of space. But this beauty is a mask. As we draw closer, the illusion of tranquility shatters. This distant world, known to astronomers as a hot Jupiter because of its immense size and its intimate, dangerous proximity to its parent star, endures conditions that transcend our wildest imagination. It is a world of violence, wrapped in a beautiful color. The atmosphere here is not the gentle blanket of air we breathe. It is a scorching, turbulent maelstrom because it orbits so tightly to its star. The temperatures here soar to terrifying heights, reaching over 1,000 degrees Celsius, that is roughly 1,832 degrees Fahrenheit. To imagine this heat is to imagine an oven capable of melting rock. a heat that is relentless and all-consuming. It is this intense proximity, this bombardment of severe stellar radiation, that sculpts the planet's nightmare atmosphere. In this hellish environment, the clouds are not made of water vapor. The heat is so profound that silicate particles, the very building blocks of sand and glass, condense in the air. But they do not form soft, fluffy white clouds. Instead, these silicates exist in a molten state, glowing and floating in the heavy, superheated sky. And then there is the wind on our gentle earth. We speak of storms with awe. We remember the hurricanes that bend palm trees and shake the windows of our homes, the most powerful winds recorded in our history. The ones that reshape coastlines might reach speeds of 250 kilometers per hour, or about 155 miles per hour. We call that destruction. We call that power. But here, on this deep blue giant, those earthly storms would be no more than a whisper, a barely noticeable sigh. The atmospheric tempests that rage on HD 189733b are of a magnitude that is difficult to truly comprehend. The winds here do not blow, they scream. They howl at speeds exceeding 7,000 kilometers per hour. That is around 4,350 miles per hour. Let that number settle in your mind for a moment. 7,000 kilometers per hour. That is nearly 20 times faster than the fiercest hurricane ever witnessed by human eyes. Imagine the air moving with such ferocious velocity that it could carry a traveler across an entire massive continent from one coast to the other in well under 2 hours. The wind here is not just moving air, it is a physical wall, a crushing force driven by the dramatic temperature differences between the planet's day side and night side. The hot air rushes toward the cooler regions with a desperation and violence that defies any earthly comparison. This wind shapes the planet's identity. It dictates the weather, the landscape, and most terrifyingly, the rain on Earth. Rain is a symbol of life. It washes the dust from the leaves. It fills the rivers. It taps gently against the window pane to lull us to sleep. But on this world, the rain is a weapon. This is the phenomenon of glass rain. It sounds like something from a dark fairy tale, but it is a scientifically documented reality born of this unique chemistry. Remember the molten silicates floating in those high-temperature clouds as they are caught in the ferocious, screaming winds. They cool, and as they cool, they harden. They do not turn into soft droplets of water. They solidify into jagged, razor-sharp shards of glass. And because the wind is so fast, this rain does not fall down. It falls sideways. Imagine a storm of millions of glass shards, flying horizontally through the air at 7,000 kilometers per hour. They bombard the atmosphere and the lower depths with the speed of bullets. It is a relentless, horizontal slash of glitter and danger. This shower of glass shapes the unseen landscape in ways we can barely fathom. If there were a surface to stand on, it would be subjected to constant, high-velocity abrasion over geological timescales. This assault might carve out vast, reflective features, perhaps dunes made not of sand, but of ground glass, sparkling ominously under the glare of the nearby star. The energy here is chaotic. The heat from the star and the kinetic energy of the falling glass create an atmosphere that is in a perpetual state of flux, forever changing, forever violent. It is a place where liquid water, the cradle of life as we know it, cannot exist. It is a beautiful, blue, uninhabitable jewel, spinning alone in the dark, leaving the violent blue winds behind. We let the current of the cosmos carry us deeper, further into the shadows. We drift about 750 light-years away from Earth, toward the constellation Draco, the dragon. Here, we find a world that challenges our understanding of light itself. This is Tres 2b. If the previous world was a deceptive jewel, Tres 2b is a phantom. It holds the title of the darkest planet ever discovered in the known universe. When we look up at our moon, it shines because it reflects the sun's light. Even a lump of coal reflects a small fraction of the light that hits it. But Tres 2b is darker than coal. It reflects less than 1% of the starlight that falls upon it. It is a shadow suspended in space. A world that seems to swallow light rather than share it. Why is it so dark? The answer lies in the thick, heavy chemistry of its atmosphere. It is a recipe for darkness. The air here is filled with a high concentration of light-absorbing chemicals. Imagine a mist composed of vaporized sodium and potassium, elements that, in this alien environment, act like a sponge for visible light. In our own solar system, we are used to clouds that reflect sunlight, making planets like Jupiter or Venus appear bright and white. But here, the chemistry is different. There are likely clouds of titanium oxide, a compound that is often used in white paint on Earth to reflect light. However, in the strange, physics-defying cauldron of Tres 2b, titanium oxide does not reflect. The conditions are such that these heavy elements absorb almost every photon of sunlight that dares to touch the planet. They trap the light. They hold it prisoner, converting it instantly into heat. This efficient absorption creates a world of profound gloom. It prevents the planet from shining back at the universe. But it is not a cold darkness. It is a hot, suffocating darkness. The temperatures here also reach up to 1,000 degrees Celsius, or about 1,832 degrees Fahrenheit. This intense heat is the engine that keeps the light-absorbing chemical reactions going. It ensures that the sodium, potassium, and titanium oxide remain in a vaporized state, forever hungry for light. Some scientists believe there is more to this mystery. They speculate that there are other, unknown compounds lurking in that deep, dark atmosphere, ingredients we have not yet identified. Chemical ghosts that are even more efficient at devouring light. These unidentified materials might be new types of matter that can only exist under such crushing pressures and temperatures, adding deeper layers to the planet's shroud. And yet, if you were to float close to Tres 2b, staring into that abyss, you might see something unsettling. It is not pitch black like a closed room. Because it is so hot, the planet emits a faint, dull red glow, like the dying embers of a fire or the coil of an electric stove. It is a demonically dim red eye staring out from the blackness. A world of shadows and heat where the light goes to die. We drift away from the shadow world now, moving toward a realm where the concept of heat is redefined entirely. We are traveling to a place where a planet is being slowly, agonizingly consumed by its own star. Welcome to Kepler 70b, This world exists in a domain of extreme intensity that challenges everything we know about planetary climates. It orbits its host star, Kepler 70, at a distance so dangerously close that it feels less like an orbit and more like a death spiral. On Earth, we complain when the temperature rises a few degrees. On Kepler 70b, the thermometer would shatter instantly. This celestial body endures temperatures that far exceed anything found on the surface of most known planets. We are talking about a heat that rivals the stars themselves. The surface of Kepler 70b can soar to temperatures between 6,700 degrees Celsius, that is approximately 12,092 degrees Fahrenheit, and 7,300 degrees Celsius, or about 13,172 degrees Fahrenheit. Pause and let that sink in. The surface of our own sun is about 5,500 degrees Celsius. This means that the surface of the planet Kepler 70b is actually hotter than the surface of the sun that gives us life. It is a world that is burning with an intensity that is almost inconceivable. This extraordinary, blinding heat is the direct result of its proximity. It is so close to its star that it is constantly bombarded by extreme levels of stellar radiation. The star fills the sky, a wall of blinding plasma, baking the planet below. This is not just a heat wave, it is a vaporization event. The rocks on the surface do not just melt into lava, they vaporize. Metals do not just liquefy, they turn into gas. The environment is so hostile that the very definition of solid ground begins to fail. The distinction between day and night has no meaning here. The planet is locked in such a tight embrace with its star that the temperature is nearly uniform across the entire surface. There is no cool side. There is no relief. Everything on the surface hovers at the absolute brink of existence. Matter here is pushed to its breaking point. It is a world where rocks and mountains are stripped of their solidity, transforming into something ghostly and energetic. The heat is so profound that the atoms themselves can barely hold together. We are looking at a world where solid matter is surrendering, dissolving, and becoming plasma. And here, within this shimmering haze, we witness the true power of intimacy between a planet and its star. On Kepler 70b, distance is a memory. The star is not a distant point of light, but a ceiling of fire, pressing down with a weight that shapes every atom of this world. It is crucial to understand that this closeness does more than just heat the air. It forges a landscape that defies every instinct we have about solid ground. On our Earth, we trust the soil beneath our feet. We trust that mountains stand still and that valleys are carved by the slow, patient hands of water and wind over millions of years. But on Kepler 70b, the ground is as fleeting as a cloud. Imagine standing on a shoreline, but instead of water, the ocean before you is made of molten iron and silicate. It glows with a blinding, white-hot intensity, and as you watch, this ocean does not just wave or crash, it evaporates. The heat is so profound that the liquid metal lifts into the air, vanishing into a metallic mist, only to condense and rain down somewhere else in this eternal furnace. The surface is in a constant state of flux, shimmering and shifting, never settling, never resting. It is a world of mirrors, reflecting the angry face of its star in pools of liquid chrome. But heat is not the only sculptor here. Gravity, invisible and silent, pulls at the planet with titanic strength. Because the orbit is so tight, The tidal stresses are immense. The star pulls at the planet's waist, stretching it, kneading the core like dough. This constant gravitational massage likely triggers volcanic activity on a scale we can barely dream of. Imagine volcanoes, not of stone, but of exotic, superheated matter, erupting silently into the vacuum, reshaping the planet every single day. If you could somehow stand on this world protected by magic or dream, the ground would feel alive, trembling and shifting under the immense forces that bind it to its star. It is a testament to resilience. The very existence of Kepler-70b challenges the stories we tell ourselves about how the universe works. For centuries, astronomers believed that planets could only form and survive in the quiet, cool nurseries of space, far from such destructive heat. Yet, here it is, a survivor. It suggests that the mechanisms of creation are far more versatile, far more robust than we dared to hope. It whispers to us that stability can be found even in the heart of the fire. And as we ponder this resilience, we realize that this world is also a prophecy. It shows us the end stages of planetary systems. One day, in the deep, distant future, many stars will expand into red giants, swallowing their inner children. Kepler-70b is a glimpse into that twilight era, a monument to survival against the odds, leaving the fire behind. We let the cosmic currents carry us away from the heat, traveling 40 light-years toward the constellation Ophiuchus. The serpent bearer, the fire fades, replaced by a deep, enigmatic blue. We are approaching a world that challenges our understanding of the most familiar substance in our lives, water. This is the super-Earth known as GJ1214b. It is a world larger than our own, but smaller than the gas giants like Neptune. It hangs in the dark, shrouded in a thick, heavy atmosphere. At first glance, you might think of it as a water world, a place of vast, deep oceans, and you would be right. But not in the way you expect. The water here is not the cool, refreshing liquid that fills our cups. Here, we encounter a phenomenon that sounds like a contradiction, a riddle whispered in the dark, burning ice. To understand this, we must dive deep, deeper than imagination usually allows. On Earth, water knows its place. It is ice when cold, liquid when flowing, and vapor when hot. But on GJ1214b, the rules of nature are bent by crushing pressure and sweltering heat. The atmosphere of this planet is dense, pressing down on the surface with a weight that is thousands of times heavier than the air of Earth. Under this immense, suffocating blanket, the oceans cannot boil away, even though the temperatures are high. Instead, the water is forced into a strange, exotic state known as a supercritical fluid. Imagine a substance that refuses to choose. It is not quite a liquid, and it is not quite a gas. It blurs the line, existing in a ghostly, twilight state between the two. It flows like water, dissolving materials and carving paths. But it also expands to fill every corner of space like a gas. It is a thick, hot fog of water, denser than any cloud, hotter than any sauna, behaving in ways that our earthly minds struggle to visualize. This is the burning ice, not a flame, not a frozen block, but a hot, dense fluid existing under pressure so intense it defies classification. Let us sink into this pressure for a moment. On Earth, we marvel at the Mariana Trench, the deepest scar in our ocean floor. Down there, the pressure is crushing over 1,086 bars. We often say it is like having an elephant stand on a postage stamp. It is a pressure that turns submarines into crushed cans. But if we turn our gaze to GJ1214b, that earthly abyss seems almost gentle. The atmospheric pressure here enters a realm of intensity that is thousands of times greater than the deepest point of Earth's oceans. Imagine the weight of 1,000 elephants, 1,000,000 elephants, pressing down on every inch of space. Under this crushing hug, water transforms. It sheds its familiar skin and becomes something alien. Studying a world like this is like trying to read a book through a thick, frosted window from miles away. The light from its parent star is overwhelming, washing out the faint, delicate signals of the planet. And yet, scientists persist. They use advanced telescopes, peering across 40 light-years of emptiness, trying to catch the spectral fingerprints of this burning ice. They build models in laboratories, trying to simulate a pressure that can turn water into a ghost, hoping to understand the secrets hidden beneath those heavy clouds. It is a slow, patient work, a conversation with the unknown that spans generations. As we rise from the depths of that strange, pressurized ocean, we find ourselves drifting again, moving further out. About 600 light-years from home, we are drawn to a tragedy unfolding in slow motion against the backdrop of the stars. We approach the planet WASP-12b in the grand library of the universe. This world is marked with a solemn title, the Doomed Planet. It is a gas giant, roughly the size of Jupiter. But its story is not one of majesty. It is a story of surrender. WASP-12b orbits its star so closely that it has been captured in a fatal, inescapable embrace. The gravity of the star is a tyrant here. It has locked the planet in a fixed gaze, a phenomenon known as tidal locking. One side of the planet is forced to face the star forever, bathed in eternal, scorching daylight, while the other side is cast into perpetual, frozen night. On the day side, the heat is unimaginable. Temperatures soar to over 2,500 degrees Celsius, that is about 4,532 degrees Fahrenheit. The atmosphere boils. But the tragedy is not just in the heat, it is in the shape. On Earth, we are used to planets being spheres perfect, round balls spinning in the dark, but WASP-12b has been deformed. The gravitational pull of the star is so strong that it has stretched the planet. It no longer looks like a ball. It looks like an egg, an elongated teardrop pointing desperately toward the master that is consuming it. This is a world being eaten alive. If you could watch this process with eyes that see gravity and gas, you would see a stream of matter flowing from the planet to the star. It is bleeding its atmosphere into the void. Observations tell us that this world is losing its substance at a heartbreaking rate, about 189 quadrillion tons every single year. The star is stripping away the outer layers, peeling the planet like a fruit. This is atmospheric escape on a cataclysmic scale. It is a slow death. But in the timeline of the universe, it is a blink of an eye. Scientists predict that within perhaps 10 million years, a mere heartbeat in cosmic time, WASP 12b, will be gone. It will be completely devoured, its mass added to the burning bulk of its star, leaving nothing behind but the memory of its orbit. This inevitable demise is a somber reminder of the violent, dynamic nature of our galaxy. Planets are not eternal. They are born. They live. And sometimes they are consumed. The study of WASP 12b is not just about understanding a distant gas giant. It is about witnessing the final act of a celestial life, a dance of gravity and fire that ends in silence. Let us remain for a moment longer in the shadow of this cosmic tragedy. We have watched the dance, but now we must lean in closer to understand the music that guides it. The observations of WASP 12b and its slow, spiraling descent into its host star provide us with something rare, a glimpse into the machinery of the heavens when the gears are turning at their most extreme. It is a fascinating, if somewhat ominous, sight. Astronomers, peering through the lenses of powerful telescopes and space-based observatories, have gathered critical whispers from this doomed world. They have collected light that has traveled hundreds of years to tell us the story of how a planet is consumed. Perhaps the most compelling part of this story comes from a visual that is almost poetic in its sadness. Sensors have detected a vast, tenuous cloud of material being pulled away from the planet. It is not just evaporating into nothingness, it is flowing. It forms a bridge, a ghostly river of gas stretching from the planet toward the star. It is as if the star is drinking the life force of its companion, siphoning off the atmosphere in a long, continuous stream. This bridge creates an extended atmosphere, a halo of lost matter that connects the predator and the prey. How do we know what this river is made of? We cannot touch it. We cannot scoop it up in a jar. Instead, scientists use a technique that feels like magic, known as spectroscopic analysis. Imagine sunlight passing through a prism, breaking into a rainbow. Every element in the universe, hydrogen, helium, iron, has a favorite color, a specific signature that it leaves in that rainbow. By catching the light from WASP 12b and unbraiding it, unraveling it like a rope to see the threads within, astronomers can read the chemical recipe of the planet. In this stream of stolen gas, they have found the fingerprints of hydrogen and helium, the lightest and most common elements in the universe. Yet, they have also found heavier elements, materials that should be deep within the planet's atmosphere, now being stripped bare and added to the burning bulk of the star. It is a transfer of essence, atom by atom. This process is violent enough to change the very shape of the world. As we mentioned, the planet is no longer round. The tidal forces, those invisible hands of gravity, are pulling so hard that the planet has become distorted. It is elongated, stretched out like a piece of taffy or a rugby ball. This distortion does more than just change how it looks. It destroys the planet's gravitational balance. It makes it easier for the atmosphere to slip away, accelerating the demise, hastening the end. As the mass is stripped away, the blanket that protects the planet becomes threadbare. The atmosphere thins, This loss changes the delicate pressure balance between the planet's surface and the cold vacuum of space. Because the star is so close, the heat is relentless, causing the remaining gas to expand, to puff up, making it even easier for it to escape. It is a vicious cycle. The thinner the atmosphere gets, the less it can protect the surface from the searing radiation of the star. The temperatures rise even higher, potentially altering the chemistry of the surface itself, baking it into new, unrecognizable forms. The changes are not just on the surface. Deep inside WASP 12b, the planet is groaning. The same tidal forces that stretch its shape are also kneading its core. Imagine bending a piece of metal back and forth until it gets hot in your hands. That is what gravity is doing to this planet. It is inducing internal heat, a geothermal fever that likely triggers volcanic eruptions on a massive scale. If we could see beneath the clouds, we might see a world reshaping itself in real time, with mountains rising and falling, and magma rivers carving new paths as the planet shudders under the strain. Studying this death spiral offers us a window into a fate that seems cruel, but is a natural part of the cosmic life cycle. It challenges what we thought we knew about stability. It reminds us that orbits are not always eternal circles. Sometimes they are spirals. Sometimes they end. From this crowded, noisy death, we seek a different kind of silence. We turn away from the heat to travel to a place of profound solitude. We are going to visit a rebel, a wanderer that refuses to follow the rules. We delve into the enigmatic case of HD 106906b. If the previous world was a story of being too close, this is a story of being unimaginably far, located about 300 light-years away from Earth, in the constellation Crux. This exoplanet presents a puzzle that keeps astronomers awake at night. In our solar system, we are used to a certain order. The planets huddle around the sun like a family around a campfire. Even Neptune, the most distant major planet, is relatively close in cosmic terms. HD 106906b, however, is situated at a staggering distance. It orbits its host star at more than 650 times the distance between the Earth and the Sun. To put that in perspective, imagine our Sun is a light bulb in the center of a room. Earth would be a speck of dust just a few inches away. This planet, it would be way down the street, sitting alone in the dark. It is so far out that it resides in a region where our traditional models of planet formation simply break down. According to the rule books we have written, a planet should not exist there. The gas and dust needed to build a world are usually concentrated close to the star. Out there, in the hinterlands, it should be empty. Yet, there it is, a massive world, 11 times the mass of Jupiter, floating in the deep freeze. It is not just the distance that is strange. It is the path. Most planets, including our own, orbit their stars on a relatively flat plane, like marbles rolling on a dinner plate. HD 106906b has a disrupted orbit. It is highly elliptical, meaning it does not move in a perfect circle, but in a long, stretched out oval. More than that, it is inclined. It is tilted significantly in relation to the plane of its solar system. It is as if the rest of its family is walking on a flat road, and this planet is climbing a steep hill, moving at a completely different angle. This inclination is a clue. It whispers of a dynamic, perhaps violent past. It suggests that this planet was not born in this lonely exile. Something happened. Something pushed it. The existence of this world poses a significant challenge to our understanding. Traditionally, we believe planets form from a protoplanetary disk, a swirling, flat pancake of gas and dust that surrounds a newborn star. The planets form within this disk, eating up the material, and they settle into orbits that are close to the star and flat, just like the disk they came from. That is the story of our solar system, the extraordinary orbit of HD 106906b. With its immense distance and its wild tilt, suggests that other processes are at play. It tells us that the universe has more than one way to make a system. So, how does a planet end up so far from home? How does it survive in such a wide, lonely loop when our theories say it should not be there? This discrepancy suggests that interactions beyond simple formation are involved. It hints at a history of chaos. Theories have been proposed, stories woven from gravity and math, trying to explain this solitude. They suggest that the early days of this solar system were not orderly and calm, but a time of cosmic billiards, where massive bodies danced and collided. One prevailing theory takes us back to the beginning. It suggests that HD 106906b did not form where it is now. It likely formed much closer to its star, in the warmth and the crowd of the inner system. Then, it got into a gravitational tug-of-war. Imagine the young system as a crowded nest. Perhaps there were other giant planets there, massive siblings jostling for space. Or perhaps there was a gravitational disturbance from an unseen companion, maybe another planet we have not yet found. Or even a failed star, a brown dwarf. Lurking in the shadows, these heavy bodies would interact. Gravity is a force that can pull, but it can also fling. In a phenomenon known as planet-planet scattering, two massive planets can come too close to one another. They swing around each other, exchanging energy. It is like a slingshot. One planet settles into a tighter orbit, while the other, the loser of this gravitational wrestling match, is kicked out. This scenario implies a violent ejection. HD 106906b was likely flung outward with tremendous force. It would have traveled through the system, a rogue world careening toward the edge of darkness. Here is the miracle: it did not leave. Usually, an event like this would eject a planet entirely, sending it drifting into the void between stars to become a true orphan. Or it might send it crashing into the star to be destroyed. In this case, the balance was perfect. The kick was strong enough to send it far away, but not strong enough to break the invisible chain of gravity holding it to the star. There is another possibility, equally intriguing. Some scientists wonder if a passing star, a stranger wandering through the galaxy, might have played a role. Stars are born in clusters, crowded nurseries where neighbors are close. It is possible that long ago, another star flew by this system, close enough to brush against the edges. Its gravity could have reached in like a hand and disrupted the orbit of HD 106906b, pulling it from its original path and placing it on this strange, tilted, elliptical course. This flyby would have been a silent, slow-motion catastrophe, altering the destiny of the planet without ever touching it. It would explain the inclination, the tilt that sets this world apart from its peers. This leaves us with a picture of a dynamic, evolving universe. The early evolution of the HD 106906 system holds clues to the violent youth of planetary families. The process of planet-planet scattering, where young worlds interact and gravitationally sling each other into the dark, could explain why this planet sits where it does. This mechanism, this cosmic game of musical chairs, often results in one or more planets being moved to wider, more eccentric orbits. It is a powerful explanation for the highly inclined, lonely path we observe for HD 106906b today, leaving the cold solitude of this exile behind. We let our imagination drift inward again, moving toward the warmth, toward the fire. We travel across 489 light-years of silent, velvet space, steering our gaze toward the constellation of Monoceros, the unicorn. Here, in the mythical hunting grounds of the night sky, we find a world that redefines the very concept of weather. This is the intriguing exoplanet known as Co-Rho T7b. It is a place where the skies do not weep water, but stone. The phenomenon here is as fascinating as it is terrifying. It is a world locked in a cycle of geological violence that creates something strangely beautiful rock showers. To understand this, we must look at where this planet sits. It is not comfortably far from its star like our Earth. It is intimately, dangerously close. Co-Rho T7b orbits its star at a distance 23 times closer than Mercury orbits our own sun. Mercury is already a scorched world, but Co-Rho T7b exists in an oven of cosmic proportions. Because of this proximity, the planet is tidally locked, meaning one side faces the star forever in an eternal, blinding day, while the other faces the void in an everlasting, frozen night. On the day side, the heat is absolute. The surface temperatures soar to 2,500 degrees Celsius, that is roughly 4,532 degrees Fahrenheit. At this intensity, the ground you stand on does not just get hot. It does not just melt into lava. It surrenders completely. The rocks, the mountains, the very crust of the planet vaporize. Imagine standing on a shore, looking out at an ocean. But it is not an ocean of water. It is a bubbling cauldron of molten silicate. And as you watch, the surface of this lava ocean steams. But the steam is not water vapor. It is rock vapor. The minerals turn into gas, rising into the atmosphere like ghosts of the mountains that used to be. This creates an environment vastly different from anything we experience on Earth. The air itself is heavy with the essence of stone, but atmospheres are restless things. They move. This rock vapor is caught in the planet's winds and carried away from the blistering day side toward the cooler night side. And this is where the magic happens. As the vapor crosses the terminator line, the border between day and night, the temperature drops significantly. The gas can no longer hold its form. It begins to cool. It condenses, just as water vapor on Earth clumps together to form clouds and rain. The rock vapor on Co-Rho T7b clumps together to form pebbles. And so, on the dark side of this world, under a sky with no sun, it rains. but it rains rocks. Imagine the sound. It is not the soft patter of droplets on a roof. It is the heavy, rhythmic clattering of falling stones. A hail of pebbles and boulders plummeting from the sky, striking the frozen surface below. It is a relentless, heavy percussion in the dark. This cycle of vaporization and precipitation, rock turning to gas, gas turning to stone, is a constant feature of this world. It is a weather system driven by the most extreme temperature difference imaginable. The gravity here plays its part too. The tidal forces between Co-Rho T7b and its star are immense. They pull at the planet, distorting its shape, preventing it from being a perfect sphere. These forces also churn the inside of the planet, creating internal heat that adds another layer of complexity to this already chaotic world. For scientists, Co-Rho T7b is more than just a curiosity. It is a live laboratory. It offers a window into processes that are simply impossible to reproduce on Earth. By observing how rocks turn to vapor and rain back down, we gain invaluable insights into the fundamental behavior of minerals. It helps us write the history of the early Earth, back when our own world was young and molten. It teaches us how atmospheres form and how the crust of a planet solidifies from the chaos of creation. Watching the stone rain of Co-Rho T7b, we learn about the atmospheric circulation of hot worlds. We understand how heat moves from a star-scorched face to a frozen back. It challenges our theories about habitability, reminding us that nature can build worlds that are hostile to us, yet perfect in their own strange, rocky logic. It expands our knowledge, helping us in the search for life by teaching us what to look for and what to avoid, leaving the heavy, clattering darkness of the rock rain. We drift 40 light years closer to home, toward the constellation of Cancer, the Crab. Here, we find a world that sparkles in the data of astronomers, a planet that appeals to the part of us that loves beauty and treasure. This is 55 Cancri E. It is a super-Earth, about twice the size of our own planet. But it is not made of simple rock and soil. Scientists have been captivated by it because they believe it might be a jewel in the truest sense of the word. The surface of this world is believed to be rich in diamonds. The hypothesis is breathtaking. 55 Cancri E is primarily made up of carbon, existing in the form of graphite, the dark, soft material in your pencil, and diamond, the hardest natural substance known, unlike Earth, which is rich in oxygen and silicon. This world is a carbon kingdom, but carbon alone does not make a diamond. You need pressure, you need heat, and 55 Cancri E has both in abundance. The immense heat from its nearby star and the crushing pressure of its own gravity act as a cosmic forge. On Earth, diamonds are rare. They are born deep, deep underground, about 150 kilometers below the surface, where the weight of the world presses down for billions of years to crystallize carbon. They are secret treasures, hidden in the dark until volcanoes push them up to us. But on 55 Cancri, this process is supercharged. The entire planet is a factory for crystallization. The process begins deep within, where temperatures are high enough to melt the carbon. This molten carbon, squeezed by the titanic gravity of the super-Earth, slowly cools and organizes itself into the perfect, rigid lattice of diamond. It is a similar process to what happens on Earth, but on a scale that is staggering. Imagine a landscape not of dirt, but of glittering crystal. Imagine mountains that catch the light of the star and fracture it into a billion prisms. The planet's exceedingly high density supports this idea. It is not a puffy gas giant made of light hydrogen and helium. It is dense, heavy, and packed tight, just like a diamond. This diamond world offers us profound insights. It tells us that the recipe for a planet is not fixed. The universe is a chef with many ingredients. When we observe 55 Cancri E, we realize that the cosmic neighborhood is filled with diversity. It underscores the fact that the material available in the cloud of dust around a young star dictates the destiny of the planets born there. In the case of our Sun, we had plenty of oxygen and silicon, so we got rocks and sand. But the star 55 Cancri was born in a cloud rich in carbon, and so its children are made of carbon. The formation of a diamond planet is a testament to the unique chemical fingerprints of stellar nurseries. It also gives us clues about the internal lives of planets. How does heat move through a diamond mantle? How does a diamond crust quake? These are questions that open new avenues for geophysics, pushing our understanding beyond the rocks of Earth. It hints at evolutionary paths we have never walked. A carbon-rich planet might evolve differently over billions of years compared to a water-rich world. Its atmosphere, its surface, its potential for supporting matter, all of it is a new story written in crystal. We leave the glittering, hard surface of the diamond world now. We expand our view. We pull back, further and further, until the planet is just a speck. We are traveling hundreds of light years away to witness a spectacle of scale, a structure so vast it defies the eye. We approach the rings of J1407b. In our own solar system, Saturn is the jewel. Its rings are the crown that makes it the most photogenic of all our neighbors. We look at Saturn through telescopes and marvel at the delicate, golden bands of ice and dust. But J1407b is here to humble us. It represents one of the most spectacular phenomena ever discovered in the realm of exoplanetary science. These rings are not just large, they are colossal. To put their scale into perspective, you have to break your understanding of size. The rings of J1407b are so expansive that they dwarf the ring system of Saturn by an astonishing margin. Close your eyes and picture Saturn. Picture those beautiful, sweeping rings. Now, imagine a ring system so vast that you could fit Saturn's entire ring system inside it, not once, not twice, but over 200 times. That is the scale we are talking about. If you were to replace Saturn with J1407b in our own sky, the rings would be visible not just at night, but during the day. They would dominate the heavens, spanning across the sky larger than the full moon. A massive arch of shadow and light. The rings of this exoplanet span nearly 90 million kilometers. That is about 56 million miles in diameter. This is roughly 200 times the size of Saturn's rings. It is a structure so large that if the planet passed in front of its star, the eclipse would not last for minutes or hours. It would last for weeks. A long, deep shadow cast by the rings would drift across the solar system. The discovery of these rings provides astronomers with a fascinating glimpse into the past. It is like looking at a photo of our own solar system when it was still under construction. These rings are likely composed of ice, rock particles, and dust, the debris of creation. But within this swirling disk of debris, there is order emerging from chaos. Just like in Saturn's rings, there are gaps. There are spaces where the rings are swept clean. These gaps suggest the presence of moonlets, small bodies, baby moons that are orbiting the planet within the rings. These are similar to the shepherd moons we see around Saturn. They are the caretakers of the rings, using their gravity to herd the dust and ice, keeping the rings sharp and defined. The sheer extent of J1407b's rings suggests that they could be the remnants of a massive collision, a cosmic accident that shattered a moon long ago. Or perhaps they are the early stages of moon formation itself. We are witnessing a moon factory in action, drawing parallels from our own solar system. The rings of Saturn have shown us how moons can be born. In Saturn's case, the ice and rock particles within its rings interact under the planet's gravitational influence. They bump into each other. They stick together, slowly, over eons. They coalesce to form moonlets, and over time, potentially larger moons. Given the sheer, incomprehensible size and mass of the rings of J1407b rings that far exceed those of our familiar Saturn in both grandeur and scope, it is plausible to suggest that within this swirling disk, something miraculous is happening. We are likely witnessing the birth of new worlds. The theory posits that within this grander scale, the same processes of accretion and moonlet formation are taking place, but played out on a canvas that stretches for millions of miles. Imagine the countless particles of ice and dust within the rings. They are not solitary wanderers. They collide in the silence of space. They bump into one another, gently at first, and sometimes they stick, like a cosmic snowball rolling down a hill. These small clumps gather more material. They grow. They gain gravity. Over time, these objects accumulate enough mass to become dominant. They begin to clear their own paths, carving wide, clean lanes through the dusty rings as they sweep up everything in their way. This is the critical step toward becoming fully fledged moons. This process is slow. It takes eons, but it is a fascinating aspect of planetary science because it provides us with a time machine. By observing J1407b, we are looking back at the history of our own solar system. We are seeing how our own moon and the moons of Jupiter and Saturn might have formed from the chaos of the early days. It is a reminder that creation is messy, slow, and beautiful. Observing such a process offers valuable data on the conditions necessary for moon formation. It tells us about the timescales involved, how long it takes for dust to become a rock, and for a rock to become a moon. It shows us how these newly formed bodies can affect the structure and stability of the rings themselves, creating ripples and waves that tell the story of their birth. But now, we must leave the swirling activity of the rings. We must travel further, much further, into the deep, quiet, cold. We are heading toward the center of our galaxy, to the constellation of Sagittarius, the Archer. Here, about 21,500 light years away from Earth, we find a world that is locked in a frozen slumber. This is the planet known as OGLE2005b, LG390LB. It has been categorized by astronomers as an ice ball planet. The name is simple, but the reality is profound. This is one of the chilliest exoplanets ever discovered in the history of astronomy. This remote world orbits its star at a considerable distance far greater than the distance between Earth and the Sun. And the star itself is a cool, red dwarf, offering little comfort. The result is a world where warmth is a stranger. The term ice ball is not an exaggeration. The surface temperature here is estimated to be around -220 degrees Celsius. That is roughly -364 degrees Fahrenheit. At this temperature, the concept of melting does not exist. Water on this surface would be as hard as rock, permanently frozen, creating a planet-wide landscape of eternal ice, unlike the gas giants in our solar system, such as Uranus and Neptune, which hide their secrets under thick layers of hydrogen and helium. This planet is thought to have a solid surface. It is a rocky world wrapped in a shell of ice. The extreme cold is a direct result of its distant orbit. It wanders so far from its hearth that it receives only the faintest whisper of solar energy. This classification provides us with deep insights into the diversity of planetary environments. It challenges our understanding of habitability. When we think of life, we think of liquid water, but here, water is a mineral, a solid part of the geology. While the harsh, frigid conditions on such a planet would seem inhospitable to life as we know it, studying these worlds helps scientists understand the outer limits of planetary climates. It helps us map the potential for water in all its various states across the cosmos. On a world this cold, the very air behaves differently. In planetary science, temperature is the architect of the atmosphere. For a planet as frozen as OGLE2005b, LG390LB, volatile compounds, things that would be gases on a warmer world, like water vapor, carbon dioxide, and methane, cannot float. They freeze out. Imagine a snow that never stops. A snowfall of the atmosphere itself. These gases turn into frost and settle on the surface. This process strips the sky bare, significantly reducing the thickness and density of the atmosphere. There is no blanket to hold in the heat. The lack of a substantial atmosphere means that any heat, whether from the distant star or from the planet's own internal core, escapes easily into space. There is no greenhouse effect here to trap warmth. It is a world exposed to the vacuum, exacerbating the cold conditions. It stands in stark contrast to planets with thick, cozy atmospheres that can maintain warmth even in the dark. And yet, this frozen silence offers insights. The absence of a substantial atmosphere and the extreme cold greatly diminish the likelihood of liquid water, that key ingredient for life on Earth. However, these conditions open up intriguing questions. Could life exist in other forms? Could there be extremophiles, life that loves the extreme hiding in the ice? Pushing the boundaries of what we believe is possible. But how do we find such a cold, dark, and distant rock located over 20,000 light years away? This planet is too faint to be seen directly. To find it, scientists had to use a technique that relies on the very fabric of space and time. This method is called gravitational microlensing. It sounds complex, but imagine it like a cosmic magnifying glass. This phenomenon occurs when a massive object, like a star or a planet, passes in front of a more distant star from our point of view. gravity, as Einstein taught us, can bend light. So, as the planet OGL E2005BLG390LB passed in front of a background star, its gravity acted like a lens. It bent and magnified the light of that distant background star for a brief moment. By watching that brightening of light, astronomers could deduce the presence of the planet. They could calculate its mass and its distance. This technique is powerful. It allows us to find planets that are too distant or too faint for conventional methods. It allows us to see the invisible, to detect cold, dark worlds that do not emit light of their own. It does not rely on the light from the planet, but on the way the planet touches the light of others. In addition to this clever observation, scientists use computer models, digital universes, to understand what life might be like on the surface. By inputting the planet's mass and orbit, they can make educated guesses about the ice, the temperature, and the thin, frozen atmosphere. Telescopes equipped with sensitive instruments, both on the ground and in space, follow up on these discoveries, refining the data, helping us paint a picture of a world we will likely never visit, but can still understand. Now, we must prepare ourselves for a shock. We are leaving the deepest cold imaginable to travel to an inferno. We are going from the freezer to the furnace. Welcome to KELT-9b, located about 670 light-years away from Earth in the constellation Cygnus. The Swan. This world holds the title of the hottest known exoplanet. The conditions here are not just extreme, they are apocalyptic. Several factors come together to create this scorching reality. First, there is the star, the host star. KELT-9 is a beast. It is almost twice as hot as our own sun, burning with a fierce blue-white intensity. It is one of the hottest stars known to host a planet. Then, there is the distance. KELT-9b orbits this blazing star with astonishing intimacy. Its orbital period is just about 1.5 Earth days. Think about that. A year on this planet lasts less than 2 days on Earth. It is whizzing around its parent at a breakneck speed, locked in a tight, dangerous embrace. This places the planet in an intense, stellar environment. It receives a colossal amount of radiation, thousands of times more than Earth receives from the Sun. The result is a temperature that defies logic. The atmosphere of KELT-9b heats up to more than 4,300 degrees Celsius. That is about 7,800 degrees Fahrenheit. Let that number sink in. 4,300 degrees. This is hotter than many stars. Most red dwarf stars in the universe are cooler than this planet. It is well above the melting point of almost every material found on Earth. You could not build a spacecraft to land here. It would vaporize before it even touched the upper clouds. Such extreme temperatures create an environment of exotic chemistry. On Earth, molecules hold together. Water stays as water. Methane stays as methane. But on KELT-9b, it is too hot for molecules to exist. The heat is so violent that it rips them apart. Molecular hydrogen, the basic building block of gas giants, is obliterated, torn into individual atoms. We are looking at a world where the air itself is being shredded by heat. There are likely vaporized metals floating in the sky clouds of iron and titanium gas. Another factor is the lack of reflection. Planets that have bright, white clouds, like Venus, can reflect sunlight back into space, keeping themselves relatively cool. But the intense heat on KELT 9b likely prevents the formation of such clouds. The heat is too great for ice or water clouds to form. So, the planet absorbs almost all the stellar radiation that hits it, getting hotter and hotter, like many of the other giants we have met. This planet is tidally locked. One side faces the star forever, the other is in perpetual darkness. While winds might carry some heat to the night side, the day side remains an inferno, showcasing the absolute extremes that nature can produce. For astronomers, KELT 9b is an irresistible target. It is a monster that demands to be studied. Future observations aim to delve deeper into this extraordinary atmosphere. Scientists dream of using the next generation of tools, the great eyes of humanity, to look closer. They are particularly interested in using advanced telescopes like the James Webb Space Telescope and the Extremely Large Telescope. The goal is to study the air of this planet in detail. They want to find those exotic, ripped-apart molecules. They want to detect the spectral signatures of vaporized metals, to see if there are elements there that are unknown or rare in cooler worlds. Given the extreme difference between the day side and the night side, scientists are also keen to understand the weather. How does heat move on a world this hot? Are there supersonic winds carrying gaseous iron from the day to the night? The James Webb Space Telescope, with its golden mirrors sensitive to infrared light, will be able to detect the thermal emission, the heat glow of the planet. It will help us map the temperature distribution. The Extremely Large Telescope, with its enormous collecting area, will offer unprecedented resolution, allowing us to taste the chemistry of the atmosphere with greater precision than ever before. Additionally, there is one more secret we wish to unlock: the magnetic field. We want to understand how KELT 9b interacts with the fierce stellar wind blowing from its host star. This interaction is crucial. It tells us about atmospheric loss, how the planet is slowly evaporating, and how these invisible magnetic forces affect the planet's long-term evolution and stability. From the blinding blue heat of the hottest planet, we let the currents of space carry us away, cooling our senses, drifting toward the constellation of Ursa Major, the Great Bear, here, about 190 light-years from Earth. We find a world that teaches us the true meaning of the word change. This is HD 80606b. If the other planets we have visited were defined by a single extreme feature, eternal darkness, rain of glass, or diamond fields, this planet is defined by the violence of its journey. It is a gas giant, but it does not walk a steady path. In our own solar system, planets are like disciplined dancers. Earth, Mars, Jupiter, they all move in nearly perfect circles, maintaining a polite and steady distance from the sun. This circular waltz gives us our predictable, gentle seasons, but HD 80606b follows a different rhythm. It moves in a highly eccentric orbit, a long, stretched-out oval that looks more like the path of a daredevil comet than a respectable planet. Imagine a diver standing on a high board, preparing to plunge. For most of its year, which lasts about 111 days, this planet lingers far away from its star, in a place called Apostron. Here, It is relatively cool, floating in the quiet outer reaches of its system. But gravity is a patient tether. It pulls the planet in, slowly at first, and then with terrifying speed, the planet begins to dive. It falls toward its star, racing faster and faster, swinging incredibly close at a point called periastron. And then, just as it seems it might crash, it whips around the star, using the momentum to fling itself back out into the dark. This unique orbital slingshot leads to one of the most dramatic weather events in the known universe. It creates seasons not of months, but of hours. As HD 80606b approaches that closest point, the periastron, it experiences a shock to its system that is unparalleled. Imagine the sun rising, but instead of gently warming the air, it explodes into the sky. The planet is subjected to a blast of intense solar radiation. In a matter of just a few hours less time than it takes for us to sleep through the night, the temperature of the planet's atmosphere skyrockets. It heats up by hundreds of degrees. This is called a flash heating event. It is not a gradual warming, it is a thermal shockwave. The atmosphere, which was calm and cool just moments before, is suddenly energized with frantic power. This rapid injection of heat drives extreme weather events that defy description. The sudden expansion of gas creates supersonic winds that scream across the planet at speeds faster than sound, racing from the day side to the night side, trying to distribute the heat. Storm systems, vast and swirling, erupt almost instantly, spanning the entire globe. These conditions are a stark, violent contrast to the weather the planet experiences when it is far away. When it retreats to the apostron, the storms settle, the winds die down, the world becomes cooler and calmer, recovering from its close encounter with fire, only to wait for the gravity to pull it back in again. The extent of these brutal seasons is further influenced by how the planet spins. If HD 80606b is tidally locked, with one face permanently staring at the star, the shock of the approach would be even more profound on that day side. But even if the planet rotates, turning its face like a roast on a spit, the rapid heating and cooling as it moves along that eccentric track would still result in chaotic, shifting seasons. Astronomers, watching from the safety of Earth, study these changes with fascination. They use the transit method, waiting for the planet to pass in front of its star, catching the starlight filtering through that turbulent atmosphere. They use radial velocity measurements to track how the star wobbles as the planet swings around it. These observations help us write the weather report for a world where summer is a momentary explosion. But this drama comes at a cost. The extreme seasonal changes on HD 80606b have significant implications for habitability. We often look for life in places of stability, places where water can sit quietly in a pond. But here, stability is a myth. The intense fluctuations create an environment that is hostile to the delicate chemistry of life. The rapid increase in temperature during the approach would destroy any chance of equilibrium. If there were water on the surface or in the clouds, the flash heating would vaporize it instantly, turning oceans into steam in the blink of an eye. And when the planet swings back out to the cold, that vapor would likely freeze, turning into ice clouds or snow. It is a cycle of boiling and freezing that never ends. A world where water can never find a home, leaving the chaotic swings of the eccentric giant. We travel now to a place that feels more like a graveyard than a nursery. We are going to visit the undead. We drift 2,300 light-years away toward the constellation of Virgo. The Maiden. Here, we find a system that challenges everything we thought we knew about where planets can survive. These are the planets orbiting the pulsar PSRB 1257 plus 12. To understand why this is so strange, we must understand what a pulsar is. It is the ghost of a giant star. Long ago, a massive star lived here. It ran out of fuel and died in a cataclysmic explosion known as a supernova. The outer layers were blasted away, but the core collapsed in on itself. It was crushed by gravity until protons and electrons merged, leaving behind a ball of neutrons only about 20 kilometers across, yet weighing more than our sun. This is a neutron star, and because it preserved the spin of the original star, it rotates, wieldy. It spins hundreds of times every second. Beams of intense electromagnetic radiation blast out from its magnetic poles as the star spins. These beams sweep across the universe like the light of a lighthouse. From Earth, we see this as a pulse. Click, click, click. A steady, rhythmic signal in the radio darkness. The discovery of planets orbiting this dead star was a shockwave in the scientific community. It was groundbreaking. It demonstrated, for the first time, that planets could exist in the most unlikely of places. What makes these worlds unique is the environment. They are walking through the ashes of a disaster. The environment around a pulsar is extremely harsh. It is filled with intense magnetic fields and radiation levels that would sterilize a human in moments. Traditional theories of planet formation tell us that planets are born in a gentle disk of dust around a young, new star, but a neutron star has supposedly cleared its neighborhood with the violence of its explosion. So, where did these planets come from? The planets orbiting PSRB 1257 plus 12, discovered in the early 1990s, include several bodies with masses similar to Earth. Their detection was a masterpiece of precision. Astronomers did not see the planets directly. Instead, they listened to the pulse, because the planets orbit the pulsar. Their gravity pulls on the dead star, causing it to wobble slightly. This wobble changes the timing of the pulses. Sometimes they arrive a fraction of a second early, sometimes a fraction of a second late. By measuring these tiny shifts in the cosmic clock, scientists realized that the pulsar was not alone. It was being danced with. This method of detection is unique to pulsar planets. It showcases the incredible diversity of techniques we use to uncover the invisible. But the question remains, are these survivors? Or are they new creations? One theory suggests that these planets are the second generation. They might have formed from the debris left over from the supernova itself. Imagine the shattered remains of the original star, creating a disk of dust and gas around the neutron core. From this graveyard of material, new worlds coalesced, rising like phoenixes from the ashes. Alternatively, they might be the cores of old stars that were captured by the pulsar's gravity, stripped of their outer layers until only the rocky centers remained. Or perhaps they are the incredibly lucky remnants of the original planetary system that somehow survived the explosion that destroyed their sun. Regardless of their origin, the discovery opened a new avenue of research. It showed us that the universe is stubborn. Planets can form or survive, in the most extreme conditions imaginable. However, survival does not mean comfort. The conditions on the planets orbiting PSRB 1257 plus 12 are starkly different from anything in our solar system. It is an environment almost beyond comparison. Think of our home. Our solar system is a place of light and warmth. Our planets orbit the Sun, a main sequence star. It is a stable, burning ball of hydrogen that provides a consistent, gentle source of energy. This light drives our photosynthesis, warms our oceans, and creates the climate that allows us to breathe. But in the pulsar system, the Sun is a city-sized ball of crushed matter, emitting beams of X-rays and gamma rays. There is no gentle sunlight. There is only the strobe light of radiation. The radiation environment here is incredibly harsh. The beams that sweep over these planets are powerful enough to strip away atmospheres entirely. They scour the surface, irradiating the rocks, potentially sterilizing the ground to a depth of several meters. On Earth, we are protected. We have a magnetic field that acts as a shield, deflecting the solar wind and cosmic rays. But the planets around the pulsar likely have little to no protection. They are exposed. Any atmosphere they might have managed to cling to would likely be thin, tattered, or non-existent, blown away by the fierce wind of particles from the dead star. The formation mechanism itself hints at a different composition. While Earth formed from a disk rich in oxygen, silicon, and iron around a young star, these pulsar planets may have formed from supernova debris, material rich in heavy elements. Perhaps even exotic matter created in the heart of the explosion. They are alien in the truest sense, built from the shrapnel of a cosmic bomb. And finally, there is the temperature. In our solar system, we have the Goldilocks zone, not too hot, not too cold where liquid water can exist. But around the pulsar, the concept of temperature is chaotic. The planets are likely subject to extreme variations. They are bathed in high-energy particles that heat them, but they lack the steady warmth of visible light. Depending on their distance from the pulsar and the intensity of its emissions, they might be frozen wastelands on one side and irradiated deserts on the other. These conditions are far removed from the relatively stable, nurturing environment found in our solar system, where the Sun's energy allows for a range of climates, for rain, for forests, and for the deep, blue oceans that cradle life. Here, in the light of the pulsar, we find only the stark, beautiful silence of the aftermath, a reminder of the resilience of matter in the face of destruction. From the stark, silent aftermath of the pulsar, we let the cosmic winds carry us back toward the vibrant, chaotic dance of the living. We travel to a place where the relationship between a planet and its star is not one of distance and cold, but of intense, overwhelming intimacy. We approach the system known as Coro T2. Here, we witness a phenomenon that challenges the old belief that stars are the sole masters of their domains. For a long time, we thought planets were silent, passive travelers, obediently following the gravity of their suns. But the exoplanet Coro T2b proves otherwise. It tells us that a planet can fight back. It tells us that a planet can touch its star. Coro T2b is a hot Jupiter, a gas giant of immense proportions. But what defines it is its closeness. It orbits its host star, Coro 2a, with a speed that is dizzying, completing a full circle every 1.7 days. Imagine a year flying by in less than 2 days. This proximity creates a connection that is electric, literal, and profound. The most striking impact of this closeness is a phenomenon known as star-planet interaction. It is a cosmic conversation carried out through gravity and magnetism. The intense gravitational pull of the planet reaches out and grabs the star. It tugs at the star's outer layers, inducing activity that we can see from light years away. Just as the moon pulls at Earth's oceans to create tides, Coro T2b pulls at the plasma of its sun. But this is on a scale that dwarfs our ocean tides. This is a magnetic tide. The planet's gravity spins up the star's magnetic field, creating star spots, massive, dark bruises on the surface of the star, and triggering violent flares. It is as if the planet is quickening the heartbeat of its parent, causing it to pulse with energy. But this relationship comes with a sacrifice. The star, in return, bathes the planet in tremendous radiation. The atmosphere of Coro T2b is heated to extreme temperatures. It swells. It expands. The heat is so intense that the planet cannot hold on to its own air. The atmosphere bleeds off into space, escaping the planet's gravity. And here is where the dance becomes beautiful and strange. As the atmosphere escapes, it forms a cloud, a torus of material that wraps around the planet. Some of this lost material falls into the star. This is a process called accretion. The planet is slowly feeding its star, transferring its own angular momentum, affecting how the star spins. It is a two-way exchange. The material lost from the planet alters the chemical composition of the star's outer layers. It changes the flavor of the light the star emits. By reading this light using spectroscopy, astronomers can find clues about what the planet is made of, even without seeing the planet directly. It is a profound realization to know the planet. We must look at the scars it leaves on its star, leaving this intense, magnetic embrace. We drift further, about 1,040 light years away, toward the constellation of Cygnus, the Swan. Here, the universe offers us a gift of pure, crystallized beauty. We arrive at HATP 7b. At first glance, this is another hot Jupiter large, gaseous, and locked in a tight orbit. But if we could descend into its atmosphere, we would witness a weather pattern that sounds like it belongs in a book of fairy tales. On Earth, clouds are made of water vapor, and rain is liquid water. But on HATP 7b, the chemistry is far more exotic. The atmosphere here is rich in a compound called aluminum oxide. On our world, when aluminum oxide crystallizes, it forms a mineral called corundum. And when corundum is mixed with trace impurities like chromium or iron, we give it different names. We call it ruby. We call it sapphire. The intense heat on the day side of the planet vaporizes these minerals. The air is thick with the gas of gemstones, but HATP 7b is a world of violent winds. Strong currents sweep this vapor from the roasting day side to the cooler night side. As the air crosses into the shadow, the temperature drops. The vapor can no longer stay as gas. It condenses. It forms clouds. But these are not the fluffy white cumulus clouds of Earth. These are shimmering, glittering clouds of corundum, and as they get heavy, they begin to fall. It rains rubies. It rains sapphires. Imagine the sight, a storm where the droplets sparkle with the red of pigeon's blood and the deep blue of the ocean. These crystals fall through the sky, perhaps melting again as they sink into the deeper, hotter layers, only to be swept back up and vaporized. Continuing the cycle, it is a jewel box world, beautiful and deadly, a reminder of the vast range of possibilities that chemistry allows when you take it beyond the comfort of our solar system. This extraordinary phenomenon is studied by watching the brightness of the planet change over time. The way the light reflects off these gemstone clouds tells us about the winds, the temperature, and the composition. It is a sparkle in the darkness that reveals the secrets of the atmosphere. From the glittering rain of gems, we move to a heavier, more industrial beauty. We travel 640 light years to the constellation of Pisces. The fish. Here, we find the ultra-hot Jupiter, known as WASP-76b. If HATP-7b is a jewelry store, WASP-76b is a forge. This planet orbits its star so closely that a year lasts only 1.8 Earth days. It is tidally locked, meaning one side is eternally roasting while the other is eternally facing the dark. The day side is a nightmare of heat, with temperatures soaring above 2,400 degrees Celsius, that is, approximately 4,350 degrees Fahrenheit. It is hot enough to vaporize metal. Specifically, it is hot enough to vaporize iron. On the day side, iron does not exist as a solid metal. It exists as a gas. The atmosphere is filled with iron vapor, rising from the molten surface. But just like on the gemstone planet, the winds here are ferocious. They carry this iron-rich air toward the terminator, the line that separates day from night. As the winds cross into the night side, the temperature crashes. It drops by more than 1,000 degrees. The iron vapor acts just like water vapor does in a cold front on Earth. It condenses. It turns into liquid. And so, on the dark side of WASP-76b, it rains molten iron. Imagine the sound of that rain. Heavy, metallic droplets falling from the sky, glowing with a dull red heat, splashing onto the surface below. It is a world of fire and metal, a planetary blast furnace. Spectroscopy has allowed us to see this happening. We can detect the chemical signature of iron vapor on the day side, but it disappears on the night side, proof that it has rained out of the sky. It is a stark, violent, and incredibly heavy reality, a world where the storm smells of welding and the rain burns. But now, after all this fire, after the radiation, the glass rain, the diamonds, and the molten iron, we need a place to rest. We need a harbor. We let the heavy metal fade behind us. We travel 100 light years toward the constellation Dorado, the swordfish. We are looking for a small, quiet star, a red dwarf. We are approaching TOI 700d. This planet captures our imagination not because of its violence, but because of its peace. It is the outermost planet in its system, orbiting a small, cool M-dwarf star called TOI 700, and it holds a promise that none of the other worlds we have visited can offer. TOI 700d resides in the habitable zone, This is the Goldilocks region. It is the distance from the star where the temperature is not too hot to boil water away, and not too cold to freeze it into eternal ice. It is just right. The planet receives about 86% of the energy that Earth gets from the sun. It is a gentle, steady warmth. The planet is roughly Earth-sized, only about 1.2 times larger than our home. This suggests it is rocky. It has a solid surface you could stand on. It is not a gas giant or a diamond core. It is a world of dirt and rock, similar to Earth, Mars, and Venus. Planets of this size have gravity strong enough to hold on to an atmosphere, and an atmosphere is the blanket that life needs. It traps heat. It distributes warmth. Like many of the worlds we have seen, TOI 700d is likely tidally locked. One side faces the red sun forever, the other is in darkness. But here, that might not be a death sentence. If the atmosphere is thick enough, it could circulate the heat. Imagine standing on the surface of TOI 700d. You would likely stand in the twilight zone, the band between day and night. The sun in the sky would be large and red, hanging motionless near the horizon, casting long, soft shadows. The light would be ruddy, like an eternal sunset on Earth. The winds might be constant, blowing from the day side to the night, but they would be gentle compared to the supersonic storms of the hot Jupiters. Crucially, the star itself is quiet. Many red dwarfs are violent, lashing out with flares that strip planets bare. But TOI 700 appears to be calm. It is a quiet neighbor. This calmness enhances the hope that life could find a foothold here. Water, liquid water, that is the dream. In this twilight world, there could be oceans. There could be lakes reflecting that large, red star. As we leave the potential sanctuary of the red twilight, we must remind ourselves that not all worlds are created equal. Some are wrapped in warm blankets of air, while others are stripped bare, left naked to the harsh gaze of the cosmos. To understand this contrast, we cast our minds 48.6 light-years away, toward the constellation of Indus. The Indian, here, orbiting a small red dwarf star, we find the barren world of LHS 3844b. This is a terrestrial planet, a rocky world that might, at first glance, remind us of our own moon or Mercury. But the conditions here are defined by a singular, overwhelming fact: the lack of air. LHS 3844b orbits its star with incredible speed, completing a full journey in just 11 hours. Imagine a year that passes in the time it takes you to finish a good night's sleep. This tight, frantic orbit places it much closer to its star than Earth is to the sun. Because of this intimacy, the planet is locked. It is tidally locked, meaning the same side always faces the star, bathed in eternal, scorching daylight, while the opposite side is cast into perpetual, frozen darkness. On Earth, we have an atmosphere. It is a wonderful, invisible river that carries heat from the warm equator to the frozen poles, moderating our climate. But observations, including those using NASA's Spitzer Space Telescope, suggest that LHS 3844b has little to no atmosphere. It is a rock in a vacuum. This absence creates a world of stark, violent contrasts. Without air to circulate the heat, the day side bakes. The rocks there are heated to temperatures of approximately 800 degrees Celsius, that is about 1,472 degrees Fahrenheit. It is a landscape of roasting stone. But if you were to step across the Terminator line into the night side, the temperature would crash without air to hold the warmth. The night side is drastically cooler. Plunging into the deep freeze of space, it is a world of two faces, one of fire and one of ice, separated by a line of eternal twilight where the silence is absolute. From the dry, silent rock, we move to a world that feels heavy, wet, and mysterious. We travel to the constellation Ophiuchus, the Serpent Bearer. About 48 light-years away, we return to the enigma of Gliese 1214b. We have touched upon this world before, but it deserves a deeper look because it represents a category of planets that is entirely alien to our own solar system. Astronomers call it a super-Earth, but let us be clear about what that name means. It does not necessarily mean it is a better Earth or a habitable one. It refers to size. Gliese 1214b is a middle child of the cosmos. It has a mass about 6.5 times that of Earth and a radius approximately 2.7 times larger. It is bigger than our rocky home, yet smaller than the ice giants like Uranus and Neptune. This classification is significant. It tells us that the universe is diverse. In our solar system, we have small rocks and big gas balls, with nothing in between. But out there, super-Earths are common. Gliese 1214b orbits a red dwarf star with a short period of about 38 hours. It is close. It is hot. But unlike the bare rock we just visited, this planet is wrapped in a thick, heavy blanket. Observations suggest it possesses a dense atmosphere, likely composed of water, vapor, or other heavy molecules. Imagine a world that is not covered in land, but in ocean. But this is not the ocean of Earth. Under the thick atmosphere, the pressure is immense. As you go deeper, the water does not stay liquid. It transforms into exotic states, hot ice, superfluid water, blurring the lines between liquid and gas. It is a water world in the most extreme sense, a laboratory of high-pressure physics where the ocean has no bottom, only a transition into a hot, dense core. Studying Gliese 1214b and its fellow super-Earths is crucial. By analyzing the light that filters through these thick atmospheres using a technique called transit spectroscopy, scientists can gain insights into their chemical recipes. They can read the weather patterns of these alien oceans, refining our models of how planets form and evolve under conditions that are vastly different from our own. Leaving the heavy, steam-filled skies of the super-Earth, we turn our gaze closer to home. In fact, we turn our gaze to our very nearest neighbor. We travel just 4.2 light-years away to the constellation of Centaurus. Here, orbiting the star Proxima Centauri, the closest star to our own sun, lies a world that carries the weight of our greatest hopes. This is Proxima Centauri b. It emerges from the data as a prime candidate in our search for extraterrestrial life. Why? Because of where it sits. This planet resides in the habitable zone of its star. We often call this the Goldilocks zone. It is that perfect ring of space where the heat from the star is not too fierce and not too weak. It is the range where conditions might be just right for liquid water to exist on the surface. And as far as we know, water is the essential ingredient for life. Proxima Centauri b gives us hope because it is Earth-sized. Estimates indicate its mass is at least 1.17 times that of Earth. This suggests it is a rocky world, a solid place where you could stand. The combination of its size and its location makes it a mirror to our own home. Tantalizingly close in the vastness of space, being so close offers a unique advantage. Proxima Centauri b is a prime target for the eyes of humanity. Future missions and powerful telescopes are being designed with this specific world in mind. We want to taste its air. We want to see its clouds. Advanced technologies, such as the James Webb Space Telescope, could provide the capability to analyze the chemical makeup of its atmosphere. We are looking for fingerprints, signs of water, oxygen, methane molecules that, when found together, could act as a biosignature, a chemical shout saying, "Something is alive here," but we must temper our hope with caution. Proxima Centauri b is a neighbor, but it lives in a rough neighborhood. Its star, Proxima Centauri, is a red dwarf. These small stars are known for their temper. They are volatile. Red dwarfs often unleash violent stellar flares, blasting their planets with high levels of radiation. For life to exist on Proxima Centauri, the planet would need to be tough. It would need a robust magnetic field, a shield to protect its atmosphere from being stripped away by the angry star. Despite these challenges, Proxima Centauri b remains a focal point. It is our nearest chance to find a reflection of ourselves. It stands there, just across the cosmic street, waiting for us to develop the vision to see it clearly. From our nearest neighbor, we take one final leap for tonight. We travel deeper into the galaxy, about 620 light-years away, to the constellation of Cygnus, the Swan. We arrive at a world that sparked a revolution in our imagination. Kepler 22b, discovered by NASA's Kepler Space Telescope. This planet holds a special place in the history of exploration. It was the first planet found by the Kepler mission to orbit within the habitable zone of a star similar to our Sun. The star, Kepler 22, is a G-type star. It is a yellow dwarf, slightly smaller and cooler than our Sun, but very much like it. This is important. G-type stars are stable. They are the steady hearths of the universe, providing a consistent, long-lasting source of energy that is conducive to the slow, patient development of life. Kepler 22b orbits in the sweet spot of this star. It receives a similar amount of light and warmth as Earth. This placement suggests a climate that could support water in liquid form, but Kepler 22b is grander than Earth. It is approximately 2.4 times the radius of our planet, categorizing it as another super-Earth. While we do not know its exact mass or composition yet, the possibilities are intriguing. It could be a rocky world with vast continents, or, more likely, it could be an ocean world. Imagine a planet covered entirely in water, a global sea with no land to break the waves, an endless horizon of blue, The concept of a planet covered in liquid water opens up fascinating possibilities for aquatic life forms in an ocean that wraps around the entire world. What kind of creatures might swim in the deep? What kind of ecosystems could evolve in a sea that never ends? The relatively gentle nature of its star suggests that Kepler-22b could maintain a stable atmosphere. Unlike the planets around violent red dwarfs, an atmosphere thick enough to trap heat through a greenhouse effect, yet not so thick that it becomes a crushing burden, would be ideal. However, the capacity of Kepler-22b to support life hinges on the details we have yet to uncover. We know where it is, and we know how big it is, but we do not yet know what it is made of. The composition of its atmosphere remains a mystery. This is where the future lies. Future observations with more advanced tools, like the James Webb Space Telescope, may finally peel back the layers of this distant ocean world. We are waiting for the day when we can detect the subtle signatures of gases that could indicate the presence of biological activity. From the hopeful blue horizons of the water worlds, we let the currents of the cosmos carry us into the realm of the strange. We are leaving behind the familiar rules of nature to visit a world that seems to delight in breaking them. We travel roughly 1,000 light-years away, toward the constellation Scorpius. The Scorpion, here, floating like a ghost in the dark, is the planet WAS P17b, discovered in 2009. This world defies conventional planetary behavior with such boldness that it has earned a nickname among astronomers, the backwards giant. It is a gas giant, vast and imposing in terms of sheer size. It is one of the largest exoplanets we have ever discovered, boasting a radius nearly twice that of our own Jupiter. You might imagine such a giant to be heavy, a crushing weight in the sky. But WASP-17b offers us a surprise. Despite its immense size, it has only half of Jupiter's mass. Think of that combination for a moment. Huge, but light. This results in an exceptionally low density. If Jupiter is a dense marble, WASP-17b is a celestial puffball, a lantern made of paper, or a dandelion seed floating in the void. It is so diffuse that it challenges our understanding of how gas giants hold themselves together. But what sets this planet apart most distinctly is not its fluffiness. It is its path in the solar system. And indeed, in most systems we observe, there is a rhythm. The star spins, and the planets orbit in the same direction, like dancers following the lead of a conductor. But WASP-17b moves to its own music. It possesses a retrograde orbit. This means it moves in the exact opposite direction to the rotation of its host star. It is the lone traveler walking upstream against the flow of the river. This is a rare phenomenon, a beautiful anomaly that challenges traditional models of how planets are born. According to our theories, planets form from a spinning disk of gas and dust, inheriting the rotation of their parent star. They should all move in harmony. The backward orbit of WASP-17b suggests a turbulent, perhaps violent past. It hints that this planet was not always a rebel. Perhaps, long ago, it had a close encounter. It might have brushed past another massive planetary body, or even a nearby star. This gravitational dance, a cosmic game of billiards, could have acted as a slingshot, flinging the planet onto a new, wild trajectory. Or perhaps it was a more gradual process, a slow, rhythmic tug of gravity known as Kozai cycles, which gently tilted and flipped the orbit over millions of years until the planet found itself moving in reverse. The atmosphere of this backwards giant is equally fascinating. Observations indicate the presence of water vapor, and possibly even carbon monoxide. But because the planet is so extended, so stretched out and thin, the weather patterns here are likely slow. Vast and deep, the intense radiation it receives from its close proximity to its star drives these mysteries, creating atmospheric phenomena unlike anything observed in our own orderly solar system, leaving the gentle, puffy giant behind. We sharpen our focus. We move from the gas to the rock, from the distant Scorpio to the constellation Draco, the dragon, situated about 560 light-years away. We find a world that serves as a bridge between Earth and the inferno. This is Kepler 10b. It orbits its host star, Kepler 10, at a remarkably close distance. In fact, it is so close that it completes a full orbit an entire year in just under 20 hours. If you were to live there, you would celebrate a birthday every single day, and the day would pass in a blink. But you could not live there. This proximity subjects Kepler 10b to temperatures that earn it the nickname, the roasting rocky world. The intense radiation from the star beats down on the surface, heating it to more than 1,300 degrees Celsius, that is, about 2,372 degrees Fahrenheit. To put that in perspective, that is hotter than fresh lava from an Earth volcano. It is a temperature that can melt iron. It can melt rock. And so, the landscape of Kepler 10b is not one of soil or sand. It is likely a lava-covered landscape. Imagine a world where the oceans are made of molten silicate, glowing with a fierce, angry red light. It is a world that is perpetually bleeding heat. This extreme environment makes Kepler 10b an unlikely candidate for hosting life as we know it. No biological cell could withstand that furnace. But for scientists, it is a treasure. It provides a unique laboratory, a place to study what happens to a rocky planet when you push it to its absolute limits. The composition of Kepler 10b is primarily silicate rock. It has a mass about 3.3 times that of Earth and a radius 1.47 times larger. These numbers confirm its status. It is a terrestrial planet. It is a cousin to Earth, Venus, Mars, and Mercury. It has a solid kinship with the ground we stand on. However, unlike the rocky planets orbiting our cool, distant sun, Kepler 10b highlights the diversity of planetary environments. It reminds us that rocky does not always mean solid. The discovery of this world was a milestone. It was significant not only for confirming the existence of rocky exoplanets, proving that Earth is not unique in its composition, but also for demonstrating the power of the Kepler telescope by using the transit method, monitoring the slight, almost imperceptible dimming of a star's light as a planet passes in front of it. Astronomers can gather critical whispers from the dark. In the case of Kepler 10b, these observations have provided valuable data on density. We know it is dense, like a heavy iron ball. This extreme proximity also raises questions about its history. It is unlikely it formed this close to the fire. It probably formed farther out, in the cool safety of the outer system, and migrated inward over time. It was drawn in by gravity, spiraling closer to the star, a process that helps us piece together the dynamic, moving story of planetary systems, including the ancient history of our own. From the molten rivers of the roasting world, we travel now to a place of paradox. We go about 33 light-years away, to the constellation Leo, the Lion. Here, we find a planet that defies logic, a world that sounds like a riddle. This is Gliese 436b. It is known as the burning ice planet. In our minds, fire and ice are enemies. Ice melts in the heat. That is the rule of nature we learn as children. But Gliese 436b breaks that rule. This planet orbits very close to its host star, Gliese 436, with a scorchingly short orbital period of just over 2 days. Because of this, the surface temperature exceeds 400 degrees Celsius. That is about 750 degrees Fahrenheit. At this temperature, water should not just boil, it should flash into steam instantly. It should vanish. And yet, the planet is covered in ice. How is this possible? The answer lies in the crushing embrace of gravity. The immense gravitational pressure on Gliese 436b is so great that it acts like a lid on a pot. It forces the water molecules to stay together, even though they are screaming with heat. It crushes the water into an exotic form of solid matter known as Ice X or Ice 10. This is not the ice you put in your drink. It is a crystal structure formed under pressure so intense that it remains solid even when red hot. Imagine a block of ice that you could not hold because it would burn your hand. Yet it would not melt. It remains solid, stubborn, and strange, creating a scenario where ice can exist in a near-stellar environment. This peculiar state of matter is a result of the planet's unique build. The atmosphere is rich in hydrogen and helium, with traces of water vapor, suggesting that water is abundant here. But due to the extreme conditions, this water enters a realm of physics we rarely see. It transforms into hot ice and supercritical fluid, a ghostly state of matter that exhibits properties of both thick liquids and expanding gases. The discovery of Gliese 436b has significantly expanded our imagination. It challenges our preconceived notions about water. It tells us that water is more versatile than we thought. The existence of hot ice suggests that the universe is full of planets with similarly exotic conditions, defying easy categorization and expanding the possibilities for what we might find in the dark. Finally, we drift to a world that is disappearing before our very eyes. We travel 150 light-years away, to the constellation Pegasus, the winged horse. We approach the tragic, beautiful world of HD 209458b, but astronomers often call it by a more poetic name, Osiris, named after the Egyptian god of the afterlife and rebirth. This planet stands out in the pantheon of exoplanets for a dramatic reason. It is evaporating. Osiris is a gas giant, orbiting its host star at a mere eighth of the distance that separates Earth from the Sun. It is dangerously close. This leads to surface temperatures exceeding 1,000 degrees Celsius, about 1,832 degrees Fahrenheit. The star is not just heating the planet, it is attacking it. The close proximity subjects Osiris to intense stellar radiation. The heat causes the atmosphere to expand, puffing up like a balloon that is being overfilled. It expands to the point where gravity can no longer hold on to it. The atmosphere starts to escape. It bleeds into space. This phenomenon of atmospheric escape was among the first of its kind to be observed directly, using the Hubble Space Telescope. Astronomers watched in awe as they detected hydrogen, carbon, and oxygen being blown off the planet. These gases are moving at speeds of thousands of kilometers per hour. They are not just drifting away, they are being torn away by a stellar wind. This creates a vast tail of material trailing behind the planet. Much like the tail of a comet, imagine a planet that looks like a comet. A giant blue sphere leaving a streak of its own life force across the sky. This escape process is significant. It is estimated that the planet may be losing about 100 million to 500 million kilograms of mass every single second. It is a world that is slowly, beautifully dissolving. The evaporation of HD 209458b provides critical insights. It teaches us about the fragile relationship between exoplanets and their stars. It shows us what happens when a planet flies too close to the flame. The intense radiation that drives this escape is also responsible for ionizing the escaping gases, lighting them up, and allowing them to interact with the star's light to produce the observable signatures that led to the detection of this phenomenon. From the evaporating tail of the dying comet planet, we turn our eyes toward a scene that feels less like science and more like a memory from a dream we all shared. We travel about 200 light-years away, toward the elegant wings of the constellation Cygnus, the Swan. Here, we find Kepler 16b. This world offers a glimpse into a reality that seems plucked straight from the realms of science fiction. For years, we watched movies where heroes looked out over desert sands to see two suns sinking below the horizon. We thought it was just a story, but Kepler 16b proves that the universe is far more creative than our best writers. This is the land of two suns. It is distinguished by its orbit around a binary star system. Most planets we know, like Earth, are loyal to a single star. But Kepler 16b is the first confirmed circumbinary planet, a world that waltzes around two stars at once. Imagine standing on a vantage point in this system. As the day ends, you would not see a single golden orb dipping below the skyline. You would see a dance of light. One star is bright and yellow, slightly smaller than our sun. The other is a small, shy red dwarf. As they move, they circle each other, casting, shifting, double shadows across the clouds of the planet. This unique celestial configuration results in a double sunset and a double sunrise. It is a spectacle of orange and red light, mixing and separating, creating a sky that is constantly changing its palette. The discovery of this world was made possible by NASA's Kepler Space Telescope, which watched the stars dim not once, but in a complex rhythm, revealing the presence of this Saturn-sized world. Kepler 16b is a gas giant, likely composed of hydrogen and helium, possibly hiding a rocky core deep within. It takes about 229 days to complete its wide loop around the pair of stars. But despite the beauty of its two suns, this is a cold place. It sits outside the habitable zone. The combined warmth of the two stars is not enough to keep water liquid. It is a frigid, gaseous world, beautiful to look at, but impossible to touch. Yet, its existence changes everything. It challenges our assumptions. For a long time, We thought the gravitational chaos of two stars would tear a young planet apart. We thought planets needed the peace of a single sun to form. Kepler 16b whispers that stability can be found even in complexity. It opens our eyes to the fact that our galaxy is full of binary stars. And now we know that those stars can have families too, leaving the double shadows behind. We drift closer, about 100 light-years away, to the constellation of Cancer, the Crab. Here, we witness a planet that is slowly undressing, revealing its true self over billions of years. This is J3470b. It is a Neptune-sized world. Classified as a warm Neptune, it is much closer to its star than our Neptune is to the Sun, and therefore, it is much hotter. But what has caught the scientific community's attention is not its heat, but its leak. The atmosphere of J3470b is escaping into space at an astonishing rate. It is evaporating. The planet orbits a red dwarf star. And although red dwarfs are small, they are active. The star blasts the planet with intense ultraviolet and X-ray radiation. This energy hits the upper layers of the planet's atmosphere, heating the gas until the hydrogen atoms are moving so fast that they break free from gravity. Imagine a giant blue balloon that is slowly deflating. The planet is losing its mass, bleeding its air into the void. This escape is particularly significant here, with estimates suggesting it may be losing up to 100 times more mass per year than other similar planets. This raises a profound question about the future. What happens when a gas giant loses its gas? We are watching a transformation that takes eons. As the thick layers of hydrogen and helium are stripped away, the planet might eventually be left with just its core. It could transform from a gas-dominated world into a rocky, Earth-like planet, albeit a scorched and barren one. This process offers us a glimpse into the life cycles of planets. It reminds us that planets are not static statues, they are evolving, changing bodies that are sculpted by the stars they love. From the leaking blue giant, we travel to a place of potential, a place that smells of rain. We move 124 light-years away to the constellation Leo, the Lion. We approach K2218b. This planet has piqued the interest of astronomers and dreamers alike. It is a super-Earth, a world larger than our home, but smaller than the giants. But what sets K2218b apart is a discovery that sent ripples of excitement through the world: the detection of water vapor. Using the Hubble Space Telescope, scientists watched as the planet passed in front of its star. As the starlight filtered through the planet's atmosphere, it carried a message. The light was absorbed in very specific patterns that can only be caused by water molecules. This was a milestone. It was the first time we found water vapor in the atmosphere of a planet orbiting within the habitable zone. The habitable zone, that magic ring, where temperatures could allow for liquid water to exist on the surface. K2218b sits right there, basking in the warmth of its red dwarf star. The presence of water vapor suggests that, under the right conditions, this planet could have clouds. It could have rain. It could have oceans. However, we must be careful with our hope. Water vapor does not guarantee an ocean. The atmospheric pressure and temperature play huge roles, and the star itself is a red dwarf, prone to flares that could make life difficult. But still, the image remains a world under a red sun, where clouds gather in the sky, and the familiar chemistry of water cycles through the air. It is one of the most intriguing targets for our future. We wait for the James Webb Space Telescope to turn its golden eye toward this world, to sniff the air for nitrogen, for methane, for the other ingredients that might tell us if this wet world is truly alive. Finally, for the last stop on our journey, we visit a world of extremes, a place where the atmosphere itself glows. We travel 900 light-years away to the constellation Puppis, the poop deck of the mythological ship Argo. We arrive at WAS Pone-21b. This is an ultra-hot Jupiter. It is a gas giant, more massive than Jupiter. But it hugs its star so tightly that it is on the brink of destruction. The temperatures here are unimaginable, but the most striking feature of WAS Pone-21b is its stratosphere. On Earth, the stratosphere is the layer of air where the ozone absorbs sunlight, causing the temperature to rise as you go higher. It is why airplanes fly there to avoid the weather. For a long time, we didn't know if exoplanets had this layer. WAS Pone-21b gave us the answer. Observations revealed that water molecules in this planet's upper atmosphere are not cooling down, they are heating up. They are absorbing the fierce radiation from the star. This creates a temperature inversion where the upper atmosphere is hotter than the layers below, exceeding 2,500 degrees Celsius, about 4,532 degrees Fahrenheit. At these temperatures, water behaves strangely. The molecules glow. They emit infrared light. If you could see this planet with heat-sensitive eyes, it would be shining like a lantern in the dark. The heat is so intense that water molecules are ripped apart. They dissociate into hydrogen and oxygen, only to recombine when they flow to the cooler night side. It is a violent, glowing cycle of destruction and rebirth. The planet is shaped like a football, distorted by gravity, and it drags a comet-like tail of escaping gas behind it. It is a laboratory of the extreme, teaching us how energy moves, how atmospheres breathe, and how matter behaves when pushed to the absolute limit. And so, we end our journey. We have traveled light years in our minds tonight. We have stood under double sunsets and watched rain made of iron. We have seen planets that are disappearing into the void and planets that hold the whisper of an ocean. We have visited the hottest fires and the coldest ice. As we return to the quiet of our own little world, we are left with a profound realization. The cosmos is vast. It is complex. It is filled with worlds that challenge everything we thought we knew. These distant worlds, with their alien landscapes and violent skies, remind us of how special our own home is. But they also remind us that we are part of something much larger. We are part of a universe that is creative, dynamic, and endlessly surprising. Let these thoughts settle in your mind like dust in a sunbeam. The universe is big, but tonight, you are safe, warm, and ready to drift away. Thank you for sharing this quiet journey into the unknown.